All right, this note takes a look at chemical bonding. In grade 11, we looked at the different types of chemical bonding, ionic bonding, polar, and pure covalent bonding. For the purposes of this course, because ionic bonding is fairly straightforward, it's just transfer of electrons to form the ions, there's electrostatic attraction, that's fairly straightforward. Molecular bonding, though, is there are some nuances to this that make it of particular interest to this course. And so that's what we're going to be looking at primarily, is covalent bonding. So let's start with a review of Lewis dot diagrams, just so that we're all on the same page with this. Remember, Lewis dot diagrams, we can use them as a short form, first of all, for showing the electron configuration of the valence shell around an atom, an ion, molecular compounds, and ionic compounds. The dots represent the valence electrons, and the inner shell is the kernel, which is just simply indicated by the symbol of the element. Just a reminder, when metal loses the valence electrons, then it forms the ion. We talked a little bit about that in the last note with electron configuration, on exactly how that works. Lewis dot diagrams are simply the, I guess, the simplest way of showing how atoms bond with each other in covalent bonds. What happens in terms of the bonding, though, is that there's always energy involved, and the potential and kinetic energy changes with how the bonding works. So, for example, if we bring two atoms together, they will get to a point, so let's start out here where they are infinitely far apart. As two atoms come closer together, the potential energy of the two atoms decreases. In other words, what will happen is that they will start to feel an attractive force to each other, and so they will start to be drawn towards each other. So the positive nucleus of the one attracts the electrons of the other one. And as that happens, they come closer and closer and closer together until they reach a kind of an optimal distance apart. And this is where the bond is actually in full force. If the two atoms try to get, the nuclei try to get closer together, then the potential energy suddenly starts to increase, and that becomes an unstable. And so at this point, the two nuclei get to the point where they start to repel each other. They start to feel those positive forces of repulsion from each other. And so that then makes them a little bit less stable. And so then they'll settle back down again until they're in this well on this potential energy diagram where they have the lowest possible energy. And that happens when they are the optimal distance apart from each other. All right, so if we can understand that, we can understand a little bit more about how the attraction of electrons to the nucleus of the opposite element is involved in this whole scheme of things, as it were. So let me just remind everybody how to draw Lewis dot diagrams. This is the kind of grade 12 version. In grade 9 and 10, you're kind of told, okay, so this is how you do it, but then you're never really told about why there are so many things that break the octet rule, and how do we know which ones break the octet rule, and all that kind of stuff. If you had me last year in grade 11, then I touched on that a little bit, and I've already taught you these rules. If not, these are the rules that you really should be following in order to draw Lewis diagrams. So let me go through the rules first, and then we'll go through an example. So the first thing is, rather than trying to figure out the whole configuration thing on which electrons go where and that kind of stuff, and which ones are shared with what, the first thing you want to do is just count all the valence electrons in all of the atoms that are involved in this molecule. Once you have that, then if there's a charge involved, because this works for the polyatomic ions, which are covalently bonded ions, add or subtract electrons for total charge of the ion. So in the case of ammonium ion, you would subtract an electron, so you just remove one. And for all the anions, the polyatomic anions, you would add the number of electrons that corresponds to the charge on that polyatomic ion. Then you write the symbol for the central atom, and if the molecule is complicated, there may be more than one central atom. But we'll start with the basic ones, and so we'll start with a central atom, place that in the middle, and then put all the other ones around it symmetrically. The specific orientation isn't really fussy or anything like that, but if you make it nice and symmetrical, then at least your diagram looks nice. Fourthly, place the bonds from each atom to the central atom. So, and each bond, we have to realize, takes up 2 electrons. Okay, so normally we do that with a dash for a Lewis dot structure. If you want to use a pure Lewis dot diagram, then just 2 dots create a pair of create the bond. Okay, so each bond takes up 2 electrons. And then we complete the octets for all the atoms except the central atom, unless of course it's a hydrogen. So hydrogen, it already has the 1 electron, so we don't need to worry about that. But any other atom, you'll complete the octet around that atom. And then if there is a central atom where there's an octet is not complete, then you may, and this doesn't always happen, especially with halogens, it won't happen, that sort of thing, but with oxygen, nitrogen, those kinds of things, we can move a pair of electrons from the octet into the spot between the atom and the central atom, and that way we create a double or maybe even a triple bond in order to complete that octet. Okay. All right, so let's do CO3 2- as an example. Carbon has 4 electrons, and each oxygen has 6 valence electrons. There's 3 of them, so we multiply it by 3, that gives us 18 electrons. And there's a 2- charge on that carbonate ion, so that's going to be 2 extra electrons for that. So that gives us a total of 24 electrons. Okay, next step, put down the central atom, so that's the lone one here, the carbon. Carbon is almost always a central atom in these types of compounds. Then the other ones, the 3 oxygens symmetrically around it. Put in a pair of electrons to create the bond to the central atom, 2, 4, 6 electrons there. And then complete the octet around each one. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. And so now we have all 24 electrons accounted for. And we have octets around each of the oxygens, but the problem is the carbon only sees 6 electrons. So now we have to take a pair of electrons from one of the oxygens, move it into the place between the carbon and the oxygen, and thereby creating a double bond. All right. Now the other thing is that, remember, this is a polyatomic ion, so there's a charge involved, right? So we put these parentheses around it and indicate the 2- charge. Now, there's something that we haven't done up till now. Well, maybe one of your teachers did this with you in grade 11. But this idea of formal charge. Formal charge allows us to determine the best possible structure for Lewis dot diagrams. In other words, sometimes there's more than one possibility here. So for example, there's this possibility here. I could move a pair into here to create a double bond. or the here and to create a double bond, or here to create a double bond. But you don't know which way is the best way to do this. And so what we do, we look at formal charge. So formal charge is simply the number of valence electrons minus the number of non-bonded electrons minus the number of bonded electrons divided by 2. All right, so in this example, we had with the carbonate ion. Let's go through this again. All right, the formal charge for this guy works out like this. So we have oxygen and there's a formal charge for each element. Okay, so for oxygen, there's 3 of them, but for each one, because they're all identical, it's going to be the valence is 6 minus 6 minus, let's see, 2 bonded pairs, so 6 unbonded pairs and 2 bonded pairs divided by 2. So 6 minus 6 is 0, minus 1 gives us a negative 1. And there's 3 of them here, so that gives us a minus 3 overall. All right, for the carbon, 4 is the valence, and there's no unbonded electrons, and there's 6 bonded electrons. Divided by 2 gives us 4 minus 3 is a plus 1. And so that gives us the overall minus 2 charge, which is fine because that makes sense. It's a 2 minus polyatomic ion. Okay, so that's supposed to work out. All right, so let's take a look at this form. So where we take a pair of electrons from one of the oxygens and move it in between a carbon and an oxygen and create the double bond. And let's figure out the formal charge for this one. All right, so for the formal charge for this one, okay, the oxygens, we got the 6 minus 2 over 2 again, which is a minus 1, but this time there's only 2 of those, so that gives us a minus 2. So this oxygen here is different, so let's look at that one. So it's 6 minus, we have this time 4 unbonded and 4 bonded. So 6 minus 4 over 2 gives us a 0. And then the carbon this time is 4 minus 0 again, because there are no unbonded electrons. But this time we have 8 bonded electrons around it. Divide that by 2 is 4, so we get 4 minus 4 is 0 as well. And so again, our overall charge is minus 2. All right, so now here is kind of the kicker. How do we know? Since there are more atoms with a formal charge of 0, this is the preferred structure. All right, so the idea is to have as many atoms as possible with the lowest formal charge as possible, or i.e. the most with a 0 formal charge. Okay, so that's what we're looking for. So that means that this structure here is preferred over the other one where we have the 3 single bonds from the oxygens to the carbons. All right, so what does that mean? Well, that gives us this particular structure. Now, here's another kicker. How do I know it's this oxygen that has the double bond and not this one or this one? And you would think that it really doesn't matter because this thing can rotate in 3 dimensions and that sort of thing. But here's the thing. So this is now kind of our theory for what carbonate ion looks like. Now remember, theory always gives way to reality. It's supposed to predict what actually happens. What we know about bond length is that single bonds have a certain length, and then double bonds tend to be shorter, and triple bonds even shorter still. And so what we have here now is an asymmetrical molecule where one bond is different from the other 2. So at least that's what the theory seems to predict. Turns out if you do an X-ray crystallography on this carbonate ion, you find that the X-ray crystallography shows us that it's in fact a symmetrical molecular conformation, which means that all the bond lengths are exactly the same. So that means that there's something in our theory that doesn't fit reality. So we don't change reality to fit the theory. We change the theory to fit reality, and that's kind of an important thing here that we need to keep in mind. So how can we massage this idea so that it fits with what we actually see in real life? Well, the way the explanation goes and the way we massage this a little is when we have a situation like this that ordinarily you would think would be symmetrical, but according to this structure looks asymmetrical. We say, okay, so what if it's not this particular oxygen-carbon bond that is the double bond? Maybe this kind of this pair of electrons here kind of flips back again, and then this pair flips in and creates the double bond here, and then this one creates the double bond here, and it flips back and forth and back and forth and back and forth so fast that the apparent result, what we observe, is that we have three identical bonds that are kind of a mix between single and double bond. Not quite either. Makes sense. Explains what we observe. And so what we get is a situation here where we've got a second structure that looks like this. And it flips back and forth between these two. Actually, we've got a third structure that looks like this, and these three flip back and forth from each other. And so we get this, what we call a resonance structure. So it's not really any one of these, it's actually a combination of all three, where the double bonds kind of flip around that central atom, and it happens so fast that the apparent result is that we get three identical bonds out of this result. Okay, so that's how resonance actually is explained. Okay, and there are lots and lots of examples where this sort of thing happens. Okay, carbonate is just one particular example that I've used here to illustrate this. Okay, anyway, we're going to spend a couple of days working out some Lewis dot diagrams and use molecular models to build some structures, and then we will hopefully get back to how this then is incorporated into what we're looking for in bonding in terms of using the atomic theory that we have just developed.